Hello everyone, welcome to my YouTube channel. In my last lecture, I was discussing about the algebra of subspaces, in which I told you that the intersection of two subspaces again form a subspace and the union of two subspaces need not be a subspace. Then I told you about a theorem, then in what cases we can say that union of two subspace will be again a subspace. So there are some conditions, that is the union of any two subspaces is again a subspace if and only if one is contained in other. That is, if you have two subspaces W1 and W2, then their union must be a subspace if W1 is contained in W2 or W2 is contained in W1. So let's see the proof of this theorem. Since this statement is if and only if, so we will prove this theorem in two parts, that is the necessary part and the sufficient part. In the necessary part, we suppose that W1 and W2 be any two subspaces of vector space V and W1 is contained in V or W2 is contained in W1. And then we prove that W1 union W2 will again be a subspace. So in the necessary part, we take suppose W1 and W2 be two subspaces of a vector space V. And either W1 is contained in W2 or W2 is contained in W1. So if W1 is contained in W2, then W1 union W2 must be equals to W1, and if W2 is contained in W1, then W1 union W2 must be equals to, in this case it will be equal to W2, and in this case it will be equals to W1. So in both the cases we are getting that the union of two subspaces is again equal to a subspace, and this implies that W1 union W2 is a subspace of V. Now we will prove the sufficient part of the theorem. In this part, we assume that W1 union W2 is a subspace of V, and then we prove that either W1 is contained in W2 or W2 is contained in W1. In this part, we take, let W1 union W2 be a subspace of V. To show, we need to show that W1 is contained in W2 or W2 is contained in W1. Now we will prove this theorem by contradiction. So we will take that let W1 is not a subset of W2. W1 is not a subset of W2. If for any of them we prove, then similarly for second one we can also prove. So I am proving for W1 and W2 that W1 is not a subset of W2. Or W2 is not a subset of W1, because we are taking both the conditions together. W2 is not a subset of W1. Since we have assumed that W1 is not a subset of W2, then there must exist some element alpha belongs to W1 such that alpha doesn't belongs to W2. And W2 is not a subset of W1, then there must exist beta belongs to W2 such that beta doesn't belongs to W1. Since both of them are not subset of each other, so that's why there must exist some elements of such type. Since And since we have assumed that W1 union W2 forms a subspace, is a subspace, then the vector addition must hold in W1 union W2. So alpha plus beta must belongs to W1 union W2. Since W1 and W2 both are subspaces also, so if I take alpha plus beta, then this must belongs to W1, or alpha plus beta must belongs to W2. Now, since W1 is a subspace, then minus alpha also belongs to W1, because every element has an additive inverse, because W1 plus forms an abelian group. So if I apply the vector addition over these two elements of W1, I'll get alpha plus beta plus minus alpha belongs to W1, and this implies beta belongs to W1. But at the start of the proof, we have taken that beta doesn't belongs to W1. So we get a contradiction. So we get from here you can write beta belongs to W1, but beta doesn't belongs to W1. So we get a contradiction. Hence, our supposition was wrong, that W1 is not a subset of W2 or W2 is not a subset of W1. So this supposition was wrong. So from here we get that W1 is contained in W2 or W2 is contained in W1. So this was the necessary and sufficient part of this theorem. I hope the proof of this theorem is clear to all of you. Now we will start to discuss the linear combination of vectors. The definition of linear combination is as follows. Let Vf be a vector space, and if alpha 1, alpha 2, alpha n belongs to this vector space V, then any vector alpha that is equals to a1 alpha 1 plus a2 alpha 2 plus plus a n alpha n, where a1, a2 and so on an are coming from the field F over which the vector space is defined, then this vector is called the linear combination of vectors alpha 1, alpha 2 and so on alpha n. So what I am doing simply, that we have a vector space from which I am taking n vectors, then with these n vectors I am defining a new vector alpha, that is the linear combination of all alpha 1, alpha 2 and so on alpha n. By linear combination means we have the scalar product. Firstly we take each element's scalar product together with a1, a2 and so on an, and then we apply the vector addition over each element. The element formed by this is called the linear combination of the vectors alpha 1, alpha 2 and so on alpha n. We equate it to a new vector alpha, and this vector alpha is called the linear combination of the remaining vectors alpha 1, alpha 2 and so on alpha n. So from here you can write alpha. This is our comma, and alpha is called the linear combination of vectors alpha 1, alpha 2 and so on alpha n. Now we will discuss the linear span. The linear combination plays an important role in the whole linear algebra, so you should understand it clearly. Let Vf be a vector space and S be any non-empty subset of V, then the linear span of S is the set of all linear combinations of finite sets of element of S. That is, suppose we have a vector space V over F, and we are taking a subset, a non-empty subset of V, S. So in S we take all the possible linear combinations of finite elements of S. That is, we choose finite number of elements of S and make the linear combination of all those elements. That type of elements will be contained in a set S, and that is called the linear span. Mathematically, we can define it as L of S. This is generally represented by Ls. This is linear span of S. This is equals to A1 alpha 1 plus A2 alpha 2 and so on An alpha n, where alpha 1, alpha 2 and so on alpha n are the elements of S, elements of finite subset of S. So alpha 1, alpha 2 dot 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 alpha n is any arbitrary finite subset of S. That is, from S we are taking any arbitrary finite set. That subset contains alpha 1, alpha 2, alpha n. With these n vectors we form a linear combination, and such linear combinations are contained in a set. That set is called the linear span of the vector space V over F. So I hope the definition of linear span is clear to all of you. In our next lecture, we will prove that this linear span forms a vector space again. So till then, please subscribe my channel. Thank you.